Hello everyone. From here we are going to start with the lecture series on the digital communication. So before to start, I am going to start with the model 3 instead of starting a model 1 and model 2, because this model is been related with respect to the earlier what we studied about the principle of communication system. So it's a little bit of the same thing, but we'll be analyzing the modulation technique in terms of a digital, that is in the bits of 1 and 0. Earlier we used to have a waveforms and all, so that what it was an analog communication. Here it is a digital modulation. Hence the same key. I'm going to start with the model 3 so that you can have a basic of this, and then you can have a grip of all the digital modulation technique and the digital communication techniques there. So here in this model 3 we'll be dealing with the some of the FSK, PSK, FSK, QPSK, DPSK. So which we broadly classify all this shift keying in terms of the coherent and non-coherent detection. So we'll see one by one as the lecture series goes on. We'll look into each of the concepts in deeply. Okay. So now with respect to the introduction to the digital modulation techniques, the first one, why do we require a, a transmission and how it is transmission over a band pass signal? Because whenever we consider, whenever we consider a signal, it has to be modulated. What is this modulation is all about? We have modifying the message signal with respect to the carrier signal, and we are mixing it up such a way that when we pass on to the channel, that is the channel, and when we get back onto the receiver side, we can demodulate, that is what we can separate the message and the carrier signal easily. This is what we call as the modulation and demodulation. Modulation is from the receiver, transmitter to receiver. Modulate is all about modifying the input, that whatever the input binary bits data sequence with the carrier signal, mix it up as per the band pass channel bandwidth available there. As per the channel bandwidth, we have to modify those things and we have to send it, and we have to send in such a way that it has to be less immune to the noise. It has to be within the frequency limits, like that it is. Usually this data can be represent the digital computer or the PCM, pulse coded modulation, which are digitized voice, video signals, etc. Like what we do usually when we call for the for example, if I'm speaking to one of my friends in a mobile phone, so I'm digitized those things. So my voice has been recorded by the microphone in the mobile phone. It has transmitted into the analog to the digital and modulated with the help of a carrier signal via antenna of the mobile phone. It has been sent to the spectrum, the channel, and it has been, that is via tower to the spectrum, and the same thing it has been received by the spectrum to the tower of my friend, and it has been detected by the antenna of my friend, and again decoded, the digitized, the demodulated, the carrier signal and the message signal has been again separated, the message signal has been decoded back to the and that is what heard by my friend at the receiver side. This is only we call as the modulation and demodulation. This complete is in one channel. So similarly, the video signals, when we do a video call, the same thing, instead of a voice, it is video signal has been sent. The channel, we know modulation, we know demodulation. The between those things, the transmitter and receiver, we require a channel. This channel might be a telephone channel. Usually when we used to have a landline, we used to have a wire there, that we call as a telephone channel. The wired channel which is connected by the telephone. Nowadays everyone has a mobile phones. Next, microwave radio link. That's what the normal days what we are using a wireless communication. Usually the telephone channel what earlier used to use was a wired communication. Microwave radio link is on the mobile phone which we are using the radiations are different, the frequency of the wavelength, so we are using it. That is what wireless communication we say. One. Next one about the satellite channel. Satellite channel is like what we use a DTA, direct to home. It is directly recharged and it is connected directly to the satellite there. Okay, directly connected to the satellite. That is what we are using. Nowadays, the geo fiber, optical fiber, that's what we are using a trend there, because we optical fiber having a high speed internet what we can be used. So geo fiber are the trending what we are using it there. The streaming or data transmission or data communication is very fast here. Okay, so among them, this is what the channels what we will be using here in the digitalization. This is the telephone channel, microwave radio link, satellite channel, and the optical fiber. Now, on basis of this, what are the basics we have analyzed? We can classify usually the basic what we use in the transmission of digital data are amplitude shift keying, that we in short we call as the ASK, frequency shift keying FSK, and phase shift keying PSK. Okay, we are going to study with these three, but in this syllabus we are dealing only with the PSK, FSK, and QPSK, and we have some basics of the offset of QPSK, MRA PSK, MRA QAM, and also in the non-current type we have deal about the DPSK and also the FSK. We'll go one by one. Usually, now for a higher data transmission through the band limited channel, combined modulation scheme are also used there. Combined, usually this is one possible thing in the digital communication where we can mix two of the modulation scheme. Among them, the amplitude phase shift keying and the quadrature amplitude modulation are used. We can mix up of those things and we can do. So as we go on with the one on the one, we can understand those things. Now, we have to deal with some of the digital modulation and demodulation scheme. In digital communication, the digital data is usually in the form of a binary, that is in terms of 2 to the power of m. Okay, so everything can be blocked and n binary bit encoded into m is equals to 2 to the power of n. The possible discrete amplitudes or m discrete phases or m discrete frequency. So whatever the m, we can write like this: 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Usually what we are using here is the 2 to the power of 1. So that is m is equals to 2, and this the model what we are doing, we call it as the m array signaling. M array signaling, and usually corresponds to the binary with a symbol 0 or 1, because its m is equals to either it is 0 or 1. So that is we call as a m. So usually we'll get into the basic three binaries by scheme. On the basis of this, either we have to symbol represent 0 or 1. So among them, first one is the ASK, amplitude shift keying. So here the amplitude of the carrier will be have a volts for binary symbol 1. That is, the amplitude will have either a for binary symbol for symbol 1 and the value 0 for symbol 0. So either, for the hence the name, it is called as a on off keying. We call this one as the on off keying, on at 1 and off at 0. The information resides only in the amplitude of the carrier signal. On the basis of the amplitude, we can classify this one as the carrier signal, either 1 or 0. Next one is the FSK. Here the carrier amplitude is fixed, but the frequency has a value f0 as that for symbol 0 and a different value of f1 hertz for symbol 1. So here when we have a symbol 1, the f1 hertz will be greater frequency, and for symbol 0 we represent here with respect to the f0 hertz, we represent with the lower frequency. So frequency f1 hertz is greater than the f0 hertz. So instantaneous frequency of the carrier switches between f0 hertz and f1 hertz corresponding to the symbol 0 and 1 respectively. So what he can conclude here, that if a symbol 0 is there, f0 hertz will be represented, and if it's symbol 1, f1 hertz is being represented. And here whatever the information lies in the frequency of the carrier, so higher frequency is there, so that time it is represented as the symbol 1, and if it is the lower frequency, so it is telling that symbol 0. Okay, this is all about the FSK. Now if it is the PSK, the phase shift keying, if the carrier amplitude and the frequency are fixed but phase has a value 0 radian for symbol 1 and pi radian for symbol 0, thus modulation process is called as the PSK or BPSK, that is we call as the binary PSK. So if it is 0, value is 0 radians, so the angle is not shifted, the angle will be whatever the same, it is same, so that time we call as a symbol 1. If it is symbol 0, then it is being represented by the pi. So that is, if any 180-degree shift is there between the two bits, the transmission, so that we can represent it as symbol 0. And here usually we represent in the terms of the phase of the carrier. So ASK, FSK, PSK, we'll see the waveforms there. Okay, and we'll analyze those things. Next. So now this demodulation can be, this is what we done with the modulation. Now demodulation, you can be doing it with respect to the two types. One is the coherent, another is the non-coherent. Coherent is nothing but we need to have a one reference name. This usually what this process we call as the demodulation process, then respectively called as the non-coherent detection, coherent detection and a non-coherent detection. In the case of the coherent detection, synchronized local reference of the transmitter signal must be available. That is, the receiver should have the same exact knowledge of the carrier wave phase reference. The receiver is said to be phase locked to the transmitter. So what we are doing here, whatever we are giving it to the transmitter and the receiver, it should have a common local reference. So what kind of the carrier signal has been given, the same thing information has to be given to the receiver. So the same thing what we give, usually we call this as the basis function here. So same thing, only the message signal will change. So what we are giving it a receiver, a transmitter, and the receiver should be having the knowledge, the exact knowledge of what we are giving it the transmitter. The same thing we have to give it to the receiver. It has to be nullify or cancelled each other. Only the message has to be passed on to the rest on end process there. So we need to have a local reference, synchronized local reference. But in non-coherent we need not require. The knowledge of the phase carrier is also not required, hence the complexity of the receiver is reduced here. This is one advantage of this one. Okay. Next, the choice of the modulation scheme is based on the following desirable requirements here. The maximum data rate. It can transfer maximum data. It shouldn't say that the capability cannot be reduced here. It should be ready to transmit any maximum. Then it should have obtained the less power, that's the transmission power. The what we say, it should have a less transmitted power there. Next one, minimum channel bandwidth. Okay, the channel bandwidth should be minimum, but it can transfer maximum data and it should utilize less transmitter power. Then minimum immunity to interfering signal, minimum immunity, so it shouldn't get interfere with the external noises there. It shouldn't be get into the external noises. Next, minimum circuit complexity. So the circuit complexity should be very less there. Should be simple circuit and which should be a minimum cost. So more the complexity, the more the cost will be. So the circuit complexity should be reduced so that it can reduce the minimum cost. Minimum probability of symbol error. So probability of error should be reduced. Like if you are sending symbol 1 and it should be credited with the symbol 0, etc., etc. So shouldn't get confused. Should have a proper boundary, proper the range, and it should be properly transmitted and properly calculation has to be done. The probability of the error should be reduced here. So we can see here the bit transmission has been 0011 0100 as in ASK. What is happening when there is 0, the amplitude is reduced to 0. See, you can observe when it is 1, the amplitude will be the A there. This is what we get, plus A minus A. So again when we go into 0, so the reduce is 0, again high, plus A minus A, 0 0 0, again the 1 and 0. That is the thing. Next is the FSK. FSK is like that. When there is a F1 and F2, two frequency has been there. When there is 0 0, the low frequency is been given. So you can see it in one bit only one cycle. F2 when a high frequency, that is for one bit 1, the two cycle has been there. So F2 is greater than F1. So higher frequency has been represented for the symbol bit 1 and lower frequency has been represented for single bit 0. So F2 is greater than F1. The higher frequency is represented for 1 and low frequency is represented for 0. Similarly, it has been carried out for low frequency, high frequency, low frequency, low frequency, low frequency, high frequency and low frequency. So that is what 0 0 1 1 0 1 0 0 0 1 0. So looking at this, I can say the above one. Now next with respect to the PSK. So it has been started with the low 0, the same thing, but when comes transition from 0 to 1, again it is started from here. The phase shift has been occurred, but till 1 it is the same thing. But when it is transition from 1 to 0, again the phase shift has been occurred. How much? By 180 degree. This is what the thing. So when it is from 1 to 1, no phase shift, so that is 0 phase shift. But from 1 to 0, 180 degree phase shift. From 0 to 1, 180 degree phase shift. So you can see it here. The same thing has been occurred. So the transition has been done from 1 to 0 here, 0 to 1 here, again 1 to 0 here. The same thing, 0 to 1 here and 1 to 0. You can observe it here. Transition from 0 to 1, 1 to 0, 0 to 1, 1 to 0 and 0 to 1 and 1 to 0. So this is how we do the analysis about the ASK, FSK, PSK with respect to the bits. So what I explained it theoretically, I am explaining here with respect to the bits here. Some random examples. So next one. This is we all deal with the whole the transmission of ASK, PSK and FSK has been represented with respect to one example, the data bit stream. Now, how we represent the signals in terms of energy? That is one question arises, because this is what the most required, and everywhere when we go derivation, this will be the same thing. So S of t is the signal, for example, and M of t is the message signal, and C of t is the carrier. This is what the S of t at the transmitter, where M of t is either 1 or 0, depending on the bit. AC cos 2 pi FCT, AC cos 2 pi FCT, the carrier signal. So I am considering one bit 1 has been transmitter 1 into AC cos 2 pi FCT. So S of t is equals to AC cos 2 pi FCT. So average power of this one, for example, average power of this one can be considered only with respect to this one, AC of t. So that is AC by square root of 2 the whole square. So that I can represent it AC square divided by 2. That is what the average power of the signal. Because whatever the message has been there has been imposed on the carrier here. So whatever the message energy has been considered with respect to the carrier signal. So this is the power consider the depending on the bandwidth. For example, the what is the amplitude of the carrier waveform has been square and divided by 2. That is what the average power. But P is equals to E by T is equals to joules per second. E is joules divided by second. So EB by TB, because here we are considering it for the bit by bit transmission. So for that purpose, I am being considered here the E by B EB divided by TB for a duration of 0 to TB here. Equating AC square divided by 2 is equals to EB by TB. I am equating this AC square by 2 is equals to EB by TB. So what I required is AC. So what I'm doing, 2EB divided by TB and square root of 2EB by TB. So therefore S of t is equals to square root of EB 2EB divided by TB into cos 2 pi FCT. So this is what the general what I'll be carrying out of all the things. So we can look it here. EB is what? So depending on this, the message energy there, whether it is 1, thus plus EB, whether it is 0, minus EB, that will be considered. This is what the S of t what will be transmitting. Okay. Now, as I said, the square root of EB, I'll take it outside. Square root of 2 by TB cos 2 pi FCT. So this is what the basics function. This is what we'll be using at a basis function, and this is what we are using as a coherent detection, the synchronized local reference. This is what the local what we are giving at the input, and the same thing we are giving at the output there. In the receiver also the transmitter, this has to be multiplied at the receiver, and also the same thing what we have giving it to the transmitter. So the when we give it a transmitter has been cancelled again when we multiply with respect to the receiver there. So what will be remaining? Only the message signal EB, square root of EB. This is what the message M of t, the square root of EB into pi 1 of t. If we have the two carrier frequency, we will be need to consider for the two basis functions, pi 1 of t and pi 2 of t. So this one will be the common, the pi 1 of t will be common for throughout the things. Okay, thank you.